Welcome everybody to my talk for the German probability and stochastics days. My name is Alexander Hinsen. I am currently a PhD student at Weierstrass Institute in Berlin, and today I would like to talk to you about the limiting shape for first passage percolation models on random geometric graphs. This is a joint project with my supervisor Benedikt Jahne, also from WIAS, with Daniel Wallesen from Groningen, and with Christian Coletti and his PhD student Lucas de Lima from Sao Paulo. First passage percolation was first introduced by Hammersley and Welch in 1965 to study the spread of fluids to a random porous medium. Since then, it has been extensively studied on the Z to the D grid, and one of the principal focuses light on the limiting shape of the growing cluster of reachable nodes from the origin as time increases. And yeah, today it's my pleasure to present to you the shape theorem for first passage percolation on Poisson-Gilbert graphs. The Poisson-Gilbert graph is one of the most fundamental spatial geometric graphs and is obtained by generating a homogeneous Poisson point process with a given intensity lambda and connecting any 2 points if their Euclidean distance is less than a certain radius r. Please note that we can eliminate one of the 2 parameters due to a spatial rescaling, as increasing the radius by a factor of alpha and simultaneously decreasing the intensity with a factor of alpha to the d leads, qualitatively speaking, to the same graph. It is as if you were looking through a magnifying glass. One of the interesting features of the Poisson-Gilbert graph is that with a given intensity, if the radius is large enough, a unique infinite component emerges. And on this infinite component, we are able to properly define the first passage percolation. For this, we assign each edge on the infinite component an identically distributed, independent, non-negative passage time. And yeah, this defines a notion of distance between 2 points on the infinite cluster. Yeah, the distance is in this case the smallest sum of the weights on a path. Yeah, in order to define a continuous version for the shape theorem, we need to we need to fatten up the process. In the case of the Z to the D, this is usually done with cubes of length 1 that are centered in D. And here, in our case, we are assigning each point its nearest point in the infinite cluster with respect to the Euclidean distance. And therefore, Voronoi cells are formed. And yeah, this extends the notion of distance from points between the infinite cluster to points to the RD, meaning the distance between 2 points is the distance of their projections on the infinite cluster. And yeah, this leads to the definition of AHT. This is a set of points whose projection are reachable from the projection of the origin by time t. And yeah, what we want to study in our shape theorem is the shape of ht divided by t, the rescaled version of it, and whether it converges. On the Z to the D grid, it is known to converge to a convex set, although the exact form is currently not known, except when the weights are constant. Due to the isomorphic nature of the Poisson point process, we over here are able to prove that yes, indeed, it converges to a ball, which is maybe not that surprising, under certain conditions that I will present to you a bit later. Okay, now a picture to illustrate the definitions. Here you can see the infinite cluster in blue and the local components in gray. As you can see, the Voronoi cells here are only generated by the infinite cluster, not by the local component. Furthermore, you're able to see one of the very problematic features of our model, meaning that 2 points that are really close in Euclidean distance, their projections can be really far apart in graph distance. You have to wander all the way around it. And yeah, to control the graph distance between points is one of the main difficulties, and one of the reasons why we are currently not why we were currently not able to extend the results to Cox point processes, for example. Okay, here is another picture made by Lucas, that visualizes the growth, in this case with a Richardson growth dynamics, meaning exponential weights. And yeah, as you can see, it really looks like a ball quite fast. Okay, now to the main result. First of all, we need exactly one spatial condition onto the graph, namely that it percolates. If the graph would not percolate, first partial percolation as we defined is not possible. Furthermore, we have two conditions on the distribution function of the weight. First of all, we have as a necessary condition that the graph of edges with weight 0 does not percolate itself. If this were the case, then after a finite amount of time, the infinite cluster of edge weight 0 edges is reached. And from this point, instantly, the whole infinite cluster is infected, and the shape theorem is not possible. Furthermore, this is a necessary condition. And furthermore, we have a moment condition. We need that a moment bigger than 2D plus 1 exists. We need this condition for our proofs. And currently it is not strict, as we are only able to prove that if the first moment, so the expectation, does not exist, then the shape theorem also does not hold. But in between the first and the 2D plus 1 moment is still open. And if those conditions are satisfied, then the rescaled version of our process is converges to a ball almost surely. Now in the remaining minutes, I would like to give you a short presentation of our proof. There are two main ingredients. Once the first main ingredient is that we have growth along a given direction. This is with the help of Kingman's subergodic theorem, we are able to prove that given a fixed direction, the speed converges to a certain value that is not dependent on the direction. Also, the main problem here is that Kingman's subergodic theorem, or Lege's version of it, only gives us the existence of the limit and not the convergence speed. So we would need uniform convergence in all directions. This is governed by our second theorem. It is a minimal growth theorem. It means that it's polynomially unlikely that a smaller ball of radius delta t is not fully infected by time t. This is achieved by controlling the graph distance with the help of a paper by Shengu and Yao. On each path, we can control the total weight on the path via Rosenthal's theorem. There we lose a factor of 2 in the moment condition. And lastly, we are able to control the number of points in the ball with the help of a theorem from Penrose. And there we lose a factor of d. So we need a moment of 2d plus kappa in order to achieve a moment condition of order of minus kappa. And those two ingredients, with those two ingredients, we can finish the proof by covering the ball with smaller balls of radius epsilon delta. And with our first condition gives us that we need 1 minus t time to reach the centroid of the ball, or the center of the ball, and then epsilon t time to reach any point in the ball. This way we can fully infect any point in the ball, and as there was a finite covering, we can fully infect the 1 minus epsilon ball. The upper bound works exactly the same. Finally, here are our references. Let me give out a shout out to Maria Deifen, who inspired our idea of the finite covering. Thank you for your attention and have a nice day.